Hey everyone, and welcome back to another explainer. I am seriously so pumped to have you here today because we are going to dive into a topic from class 9th mathematics that literally blew my mind the first time I saw it. We're exploring a realm of math that, for a long time, people thought absolutely shouldn't exist. Yet today, this exact math powers your cell phone and the entire electrical grid. We're talking about complex numbers. So if you've ever felt like math is just this rigid, unbreakable set of rules, well, prepare to have your perspective totally shifted.
All right, let's kick things off with what seems like a ridiculously simple question. What happens when you square a number? Think about it for a second. If you take a positive number, like 3, and square it, 3 times 3, you get a positive 9. But what if you take a negative number? If you multiply negative 3 by negative 3, those negative signs cancel out, right? You still get a positive 9. So our core assumption in standard algebra is that squaring any real number, literally any of them, will always yield a positive result. Keep that rule locked in your brain for a minute.
And boom! This is exactly where mathematicians hit a massive brick wall. Just look at this harmless-looking equation. X squared plus 1 equals 0. It looks innocent enough, right? But if you actually try to solve for x, you have to subtract 1 from both sides. That leaves you with x squared equals negative 1. Now, to isolate x, you have to find the square root of negative 1. But wait a minute. We literally just established that no real number, when multiplied by itself, can give you a negative result. So under the normal rules of real numbers, this equation is completely impossible to solve. It's a total mathematical dead end.
So here is our roadmap for today's explainer to see how we get out of this mess. First, the impossible equation. Second, the anatomy of complex numbers. Third, the complex conjugate. Fourth, equality of complex numbers. And finally, basic complex operations. Let's jump right in. Starting off with Section 1, the impossible equation and the entry of the imaginary unit.
So, how did they fix this broken system? Well, to overcome this massive inadequacy of real numbers, mathematicians literally just invented a brand new mathematical entity. They introduced the imaginary unit, denoted by the little letter I, basically as a patch for this bug in the matrix. Fun fact, even the legendary mathematician Descartes called them imaginary as an insult, but hey, the name stuck. Okay, so what exactly is this iota, or I? By definition, I is equal to the square root of negative 1. And because it's defined that exact way, it has this totally unique property where I squared equals negative 1. I know, it sounds a bit like science fiction. It's obviously not a real number you can count on your fingers. But by defining this imaginary unit, mathematicians suddenly unlock the ability to solve every single algebraic equation structured like x squared plus a equals 0. It was basically the master key that opened a whole new universe.
Moving right along to Section 2, Anatomy of Complex Numbers, where we start blending the real and the imaginary.
When you build a complex number, which is usually represented by the letter z, it takes the standard form of a plus ib. It's basically a mashup of two completely distinct pieces that live side by side, but they never actually mix. The a is what we call the real part, denoted as rz. The b, which is the number clinging onto our imaginary unit I, is called the imaginary part, denoted as imz. Think of it kind of like a 2D coordinate map used in video game graphics or radar systems. You need both the horizontal real direction and the vertical imaginary direction to know exactly where you are.
Let's ground this with a super quick example straight from the textbook. Take the complex number z equals 3 minus 2i. Honestly, it's incredibly straightforward to break this apart once you know what you're looking for. The real part, that standalone number right there, is 3, so res z equals 3. The imaginary part is just the coefficient attached to the I. In this case, that's negative 2. So imz equals negative 2. It really is that simple to dissect.
All right, Section 3, the complex conjugate, or as I like to call it, the mirror image.
Finding a conjugate, which we denote by just slapping a little horizontal bar over the z, is unbelievably simple. All you do is flip the mathematical sign of the imaginary part. That's it. You leave the real part completely alone. So if your number is a plus ib, the conjugate becomes a minus ib. If it's 3 plus 4i, boom, it becomes 3 minus 4i. Even if you see it written in that ordered pair format like a comma b, it just turns into a comma negative b. You are literally just flipping the sign of the imaginary universe. Which actually brings us to this really neat logical little trick mentioned in the text. What do you think happens if you take the conjugate of a conjugate? Well, if you flip a mirror image again, you're right back to looking at the original, right?
The conjugate of z bar is simply z. If you flip the sign from a plus to a minus, and then you just flip it from a minus back to a plus, you end up exactly where you started.
Okay, on to Section 4, Equality of Complex Numbers, and how we balance these new scales.
Now, the core rule here is incredibly strict, but it makes perfect sense. Remember how I said the real part and the imaginary part don't mix? They're like apples and oranges. Because of that, two complex numbers are equal if and only if their respective parts match perfectly. So if a plus ib is going to equal c plus id, that strictly mandates that the real part, a, must equal the real part c, and the imaginary part b must equal the imaginary part d. Both sides of the scale have to balance completely independently of each other.
Let's actually work through a textbook example together to see how this plays out in practice. Say we're given the equation 4x plus 3yi equals 16 plus 9i, and we need to find x and y. Step 1, we just equate the real parts, so 4x has to equal 16. Step 2, we equate the imaginary parts, so 3y has to equal 9. Step 3, we just solve those two super simple algebra equations. Divide 16 by 4, so x is 4. Divide 9 by 3, and y is 3. Turns out, complex algebra is really just a logical checklist.
Finally, Section 5, Basic Complex Operations. Time to learn the actual rules of the realm.
Now, looking at the official textbook formulas for adding and subtracting these complex numbers, it might look like a messy alphabet soup of letters and parentheses at first glance. But I promise you, the logic here is wonderfully straightforward. It all just comes back to treating those real and imaginary parts as totally separate entities.
Adding complex numbers is quite literally just grouping like terms. If you start with a plus ib and you want to add c plus id, you absolutely do not jumble them all together. You take the real parts, a and c, and add those together. Then you take the imaginary parts, b and d, and add those together, making sure to keep the I attached. Your final result is simply a brand new complex number where the real parts merged and the imaginary parts merged. Let's put some actual numbers in there so you can see how satisfying this addition rule really is. Let's say we add z1, which is 6 plus 9i, to z2, which is negative 1 plus 2i. First up, group the real numbers. 6 plus negative 1 gives us 5. Next, group the imaginary coefficients. 9 plus 2 gives us 11. Put it all back together into our standard format, and our final sum is 5 plus 11i. See? It flows perfectly.
And you know what? Subtraction follows the exact same logical pattern, keeping those two universes strictly separated. If you're subtracting one complex number from another, you just subtract the real parts from each other to get a minus c, and you subtract the imaginary parts from each other to get b minus d.
Let's tackle one last textbook example, this time for subtraction, just to be thorough. We're starting with z1 equal to negative 7 plus 2i, and we're going to subtract z2, which is 4 minus 9i. First, subtract the reals. Negative 7 minus 4 gives us negative 11. Now be super careful with the signs on the imaginaries here. We're doing 2 minus a negative 9. That mathematically flips to 2 plus 9, which is 11. So our final difference is negative 11 plus 11i.
And there you have it, guys. We started this explainer looking at what seemed like a total mathematical dead end, an impossible equation that straight up defied the basic rules of real numbers. But just by introducing a single imaginary unit, iota, we mastered an entire new number system. We can build them, conjugate them, equate them, and do algebra with them. And honestly, thank goodness mathematicians did this, because without this imaginary math, we wouldn't have modern electrical engineering, quantum physics, or even advanced computer graphics. It really makes you wonder, if inventing a new, fake number can actually build the modern world we live in today, what other mathematical rules out there are just waiting to be completely rewritten? Thanks so much for joining me on this explainer, and remember to keep questioning everything you